Have you ever felt small looking up at the night sky? It's a classic human experience. You see countless stars, each a sun, many with their own planets. Our galaxy, the Milky Way, has hundreds of billions of them, and there are hundreds of billions of galaxies out there in the observable universe. But what if our little corner of the cosmos is unusually empty? Not just a pale blue dot, but a pale blue dot in a vast cosmic desert. This isn't science fiction. It's a real scientific possibility that could change how we see our place in the universe. The universe isn't evenly filled, it's lumpy, with superclusters of galaxies and in between vast empty spaces. These are the great cosmic voids, and we might just be living inside one. Imagine the universe as Swiss cheese. The cheese is where the galaxies are, but the holes, the voids, define the structure. For decades, astronomers thought Earth was in an average part of the cosmos. But new evidence suggests our Milky Way may reside in a region with far fewer galaxies than average. This could be the key to solving one of the biggest mysteries in modern cosmology. So let's embark on a journey to the edge of what we know. We'll explore these cosmic voids, great expanses of nothingness that dominate the universe's volume. We'll look at clues in the oldest light in the cosmos and the brilliant explosions of dying stars. We'll confront a deep puzzle about how fast our universe is expanding. And we'll ask, are we adrift in a great cosmic void? Whatever the answer, it reminds us the universe is always more complex and mysterious than we imagine. Keep looking up. When we talk about a void in space, we don't mean absolute nothingness. Even the emptiest parts of space are alive with quantum particles and ancient light. A cosmic void is simply a region with far less matter, fewer galaxies, less gas, less dark matter than average. Think of it like the difference between a bustling city and the empty stretches of the Sahara. Voids are colossal, spanning tens to hundreds of millions of light years across. Our Milky Way is just a speck compared to these vast regions. Along with filaments and clusters, voids make up the cosmic web, the universe's large-scale structure. Inside a void, the night sky would look much emptier, with far fewer galaxies visible. The universe would feel profoundly isolated. These voids aren't anomalies. They're a natural result of how gravity shaped the universe after the Big Bang. Tiny fluctuations in the early universe grew into dense clusters, leaving emptier regions behind. Voids are a fundamental feature of our cosmic architecture. They help define the universe's structure, just as much as the galaxies themselves, and we may be living in one. Let's bring this idea home. Astronomers mapping our cosmic neighborhood have found a curious pattern. Our Milky Way might be inside a vast, underdense region called the KBC void, or local hole. This void is estimated to be about 2 billion light-years across, one of the largest ever discovered. We're not at the center, but we're well within its boundaries. Our local patch of the universe appears to be about 50% less dense than average. Scientists built 3D maps by measuring the redshift of hundreds of thousands of galaxies, revealing this enormous underdense region. It's like taking a census and finding most residents live on the outskirts. Living in this local hole changes our gravitational environment. In denser regions, the gravitational pull from neighboring galaxies is stronger. Inside a void, the pull is weaker, and the matter on the edge can even tug us outward. This subtle effect, void outflow, could be a crucial piece of a much larger cosmic puzzle. It's not just a quirky address, it might help explain one of cosmology's biggest mysteries. Our location could be affecting how we measure the universe itself. And that's a puzzle cosmologists are eager to solve. The question is, how much does our cosmic neighborhood matter? Now we reach the heart of the mystery, the Hubble constant. This number tells us how fast the universe is expanding right now, but different ways of measuring it give two different answers. One method looks at the early universe using the cosmic microwave background, the afterglow of the Big Bang. This predicts an expansion rate of about 67 kilometers per second per megaparsec. The other method uses nearby exploding stars, type Ia supernovae, as standard candles, giving a higher value, about 73. The gap between these numbers is called the Hubble tension. At first, scientists thought it was a measurement error, but as data improved, the tension only grew. The odds of this being a fluke are now less than 1 in a million. Something doesn't add up. Either our measurements are flawed or our understanding of the universe is incomplete, and that's where the void comes in. To understand the Hubble tension, let's look at how we measure the universe's expansion. Locally, we use the cosmic distance ladder Cepheid variable stars and Type Ia supernovae. Cepheids pulse in a way that reveals their true brightness, letting us measure distances to nearby galaxies. Type Ia supernovae are even brighter, visible across vast distances, and serve as standard candles for the distant universe. By calibrating supernovae with Cepheids, we build a ladder to measure the universe's expansion rate, yielding the higher Hubble constant. The other method looks at the cosmic microwave background, the oldest light in the universe. The CMB contains tiny temperature fluctuations, hot and cold spots, that act as a standard ruler. By measuring how big these spots appear today, we infer the universe's geometry and expansion history. This method predicts a slower expansion rate. Both methods are precise, but they don't agree. That's the Hubble tension. Two accurate measurements, two different answers. The question is why? Could our location in a cosmic void be skewing our local measurements, or is there something deeper we're missing? The answer could reshape our understanding of the cosmos. Let's dive deeper into the early universe measurement. The key is something remarkable: sound waves from the Big Bang. The early universe was a hot plasma where pressure waves, sound, could travel. These waves, created by tiny quantum fluctuations, rippled through the plasma for hundreds of thousands of years. When the universe cooled and became transparent, these sound waves froze in place. The imprint of these waves is visible today as baryon acoustic oscillations, or BAO. In the CMB, we see them as the characteristic size of hot and cold spots. In the distribution of galaxies, we see a preferred separation distance, about 500 million light-years. Measuring this scale at different times gives us a powerful, independent tool to map the universe's expansion. BAO measurements confirm the lower value for the Hubble constant. So, the tension remains. Local measurements say one thing, the early universe says another. The mystery deepens. Could our cosmic address be the missing piece? So, what if both Hubble constant measurements are right? If we live in a giant cosmic void, the matter at the edge could be pulling us outward, adding an extra outflow velocity to our local measurements. When we measure distant galaxies, we might be overestimating the universe's expansion because we're not accounting for our own local motion. Recent research suggests that a void the size and underdensity of the KBC void could explain the entire discrepancy. Our local bubble would be expanding faster than the global average, making our measurements higher. Meanwhile, the CMB and BAO, which average over the whole universe, reflect the true, slower rate. This solution doesn't require new physics, just a new perspective on our cosmic address. It's an elegant idea. Maybe we're not in an average spot after all. The void hypothesis turns a crisis into a question of geography. But is it the whole story? The debate is far from settled. More evidence is needed, and the search continues. The void hypothesis is intriguing, but not everyone is convinced. It challenges the Copernican principle, the idea that we're not in a special place. Some scientists argue the KBC void isn't big or empty enough to explain the full Hubble tension. Other evidence, like galaxy flows, doesn't clearly support a massive void. Proving the void hypothesis requires multiple independent lines of evidence. That's why scientists are exploring other solutions. Some theories propose early dark energy, a new form of energy that briefly existed in the early universe. Others suggest dark energy strength might change over time, or that new particles or forces are at play. These ideas are more speculative, but the Hubble tension is stubborn. The void hypothesis remains a conservative, if controversial, option. The real answer may involve new physics, cosmic geography, or both. The mystery is driving cosmology into new territory. So where does this leave us? The Hubble tension is real, a crack in our standard cosmological model. The idea that we live in a giant void is a serious, if debated, contender. The path forward is clear. We need more data and better maps of our local universe. New telescopes like the Vera Rubin Observatory and Euclid mission will soon revolutionize our view of the cosmos. They'll map billions of galaxies and discover thousands of new supernovae. This data will help confirm or refute the void's size and emptiness, and measure the Hubble constant with greater accuracy. If the void hypothesis is right, it would shift our perspective, reminding us that our location matters. Whether the answer lies in cosmic geography or new physics, the journey is what matters. This puzzle is pushing us to be more creative and to question our assumptions. there are still great mysteries out there waiting to be solved. So next time you look up at the night sky, ponder your place in it all. The cosmos is calling, and our job is to keep listening.